So, hello viewers, welcome back to this course. So, today we are going to start with the lecture number 16. So, and we are going to extend the Laplace transformation, because in the last class we have started with the Laplace transformation, and then we found that how the Laplace transformation is useful for transferring the differential equation into the algebraic system, algebraic equation. So, we will go further, and today I will discuss some another properties of Laplace transformation. So, we know that Laplace transformation. Now, I have that my function, suppose I have a function f t, and that is piecewise continuous and is of exponential order defined from 0 to infinity. Then I know that, so my t belongs to, then I can take the Laplace transformation of f t, that is from f t dt, and we say that the Laplace transformation exists provided that this integral exists. So, now, so in the last class we have discussed few properties of the Laplace transformation. So, today we are I am going to introduce that what about the derivative of f s, because this is, you know, that this is equal to f s. So, what we will get from here? So, let us start. So, you can call it as a property. Now, this is my equation number 1. So, I have my Laplace transformation for f t 0 to infinity e raised to power minus s t f t dt. So, what I do is that, so this is my equal to f s. Now, I differentiate both side with respect to s. So, on the left side I will get dfs over ds, and this is equal to d by ds from 0 to infinity dt. Now, so from here, so by the Leibniz rule I can take this differentiation inside, and this will become do dfs over ds. So, that will be integration. So, it will be the differentiation of e raised to power minus s t, because we are taking that differentiation with respect to s. So, f t will be same, and then dt. So, from here if I take the derivative of this one, so it is e raised to power minus s t, and the derivative of this one with respect to s, so it will be minus t f t dt. So, from here, because I am taking the derivative with respect to s, so I will take the derivative of this exponential only. So, exponential is this one, and then derivative. So, from here I will get from 0 to infinity e raised to power minus s t, and then inside I will get minus t f t. So, this factor is increased, that is minus t dt. So, from here I can say that this is a Laplace transformation of minus t f t. So, this is a Laplace transformation of minus t f t. So, from here I can say, that the Laplace transformation of minus t f t is equal to d of f s by ds, provided I already know the Laplace transformation of f t. So, for example, so let us take one example, that suppose I want to take the f t, I just take E t, then I know that f of s will be the Laplace transformation. So, this will be s minus 1. So, that is the Laplace transformation of E t. Now, I want to find the Laplace transformation of t e raised to power t. So, this one I want to find, and I do not know any formula related to any function multiplied by t, because why we are doing, as I told you, that we are going to solve the differential equation, and in the differential equation you know that the coefficient can be a constant and can be a function of t. So, whenever you have a constant function, that is okay, but whenever you are multiplied by some function of t, then you have to take the Laplace transformation of that factor also. For example, in the differential equation, suppose I have y double dash plus t y dash plus t square y is equal to sum f t, and then I have to take the Laplace transformation. So, in that case I should be able to find the Laplace transformation when I multiply by t. Here also I multiply by t, here I multiply by t square. So, this way I should be able to find the Laplace transformation. So, from here I want to find the Laplace transformation, then I will apply this formula. So, what I will do, I will take the f s is given to me, then I take the derivative of with respect to s, I will take the derivative. So, it will be, if you see, this will be equal to, so I take this one in the numerator. So, s minus 1 minus 1. So, this will be equal to minus 1 over s minus 1 square. So, from here, by this property I know that the Laplace transformation of t e t will be equal to minus of d f s by d s, and this is minus and minus. So, it will be 1 over s minus 1 whole square. So, from here we are able to find the Laplace transformation of a function t e raised to. So, similarly, I just want to use another way, that I want to find the inverse of the Laplace transformation. For example, I have my f s, and that is given to me minus 4 s divided by s square plus 4 whole square. So, this is given to me, and I want to find my f t such that the f s is the Laplace transformation of my f t. So, my question is that what is my f t? And now, from here if you see carefully, I have a factor s square plus 4, but I have the power square. It means I can remember that, okay, somewhere we have taken the derivative of 1 over s square plus 4, because I take the derivative, it becomes the square, and the power will become square, and if I take one more derivative, it becomes cubic. So, like this one. So, from here what I do is that, first of all I will find out that what is my, so this one I can write as, from here I can see that minus 4 s by s square plus 4 square. Just check that if I take the s square plus 4, and then I just try to find the derivative of this one. So, let us take the derivative of this one. So, if I take the derivative of this one, so this will be 2, and then s square plus 4 minus 1, and then d by ds. So, this one I am taking. So, it will be 2 and then minus 1 by s square plus 4 whole square into derivative of this one into 2s. So, from here I can say that this is equal to minus 4s s square plus 4 whole square. So, from here I can say that my Fs is, in this case it is a derivative of 2 over s square plus 4. So, this is given to me. Okay. So, from here I can say that this is equal to d by ds of some gs. So, what is my gt? So, gt you know that this is equal to 2 times, so it is a cos 2t. So, that is a cos 2t. So, this is equal to the cos, not cos, it is a sine basically, sine 2t. So, from here I can say that my f t will be minus t sine 2t. So, that is my answer. So, f t will in this case will be minus t sine 2t, because if I multiply it by minus t and then I take the Laplace, then the Laplace I will get from there. So, this is the example just we have taken. Now, I will try to find out another one, and I will define what about the integration of the Laplace transformation. I have just taken the differentiation, now I will take the integration. Integration of the Laplace transformation. So, in this case I just want to define what will be the integration of the Laplace transformation. So, let us do that one. So, let my f t is a piecewise continuous function as defined for the t belongs to 0 to infinity and be of exponential order. So, that we already know. Then I know that let L of f t is equal to f s. So, I have the function f t is a piecewise continuous for t belongs to this and of exponential order, and such that Laplace of f t is f s, then Laplace of f t by t. So, f t by t, so this will be equal to s over infinity s star ds star. So, in this case I am just integrating the function f s from s to infinity. So, this is there provided limit t tends to 0 from the right hand side, f t over t is finite or exists, because if this limit exists, because this function as t tends to 0, 1 over t is going to be unbounded, it is going to be infinity. So, in that case we say that if this both the functions together put the limit and then that limit comes finite, then we can define this function and then we can take the Laplace transformation. So, this is in this case I am taking the integration of the Laplace transformation. In the previous one I have taken the derivative of the Laplace transformation, and in that case we got minus t into f t, but now I am taking the integration. So, this is the proof we can do very easily, that so I have my L of f t, that is my f s is 0 to infinity e raised to power minus s t f t dt. Now, so this is 1, Now integrate both side with respect to s from limit s to infinity. So, this is the limit we are taking. So, on the left hand side I will get my s to infinity f of s star, I just put d s star, and on the right hand side I will get s to infinity and then 0 to infinity e raised to power minus s t f t dt ds star. So, this is the integration I have taken from both sides. Now, from this one, so this is the limit we are taking, and here I am taking the integration with respect to s. So, this factor is there, other factors I can take outside and I can interchange the order of the integration. So, the order of the integration if you change, in this case it will be from s to infinity e raised to power minus s star t d s star and then the remaining f t dt. So, this will be there, okay, because in this case the t is moving from 0 to infinity and s star is moving from s to infinity. So, if I change this in order of integration, you can check. So, this s to infinity I can take inside and then this will be 0 to infinity. Okay. So, from here then if I do this one, so I am taking the integration with respect to s. So, if I take the integration, it will be e raised to power minus s star t divided by minus t. So, divided by minus t, because I am taking the integration with respect to s star and then putting the limit s from s to infinity f t dt. And if we further solve this one, so from here I will get my integration from s to infinity so this one I can write as, and now put the limit. So, from 0 to infinity I am putting the limit here. So, it will be, I can take the minus sign inside outside. So, from here I can take limit s star tends to infinity e raised to power minus s star t minus e raised to power minus s t, and this one I can write as a f t divided minus t dt. So, I am putting just the limit here, and from here I will get this thing on same on the left hand side and on the right hand side. So, this factor you know that we are always taking the s is greater than some number, positive number. So, this is going to be 0 here. So, from here I will get 0 to infinity, minus sign and minus sign will cancel out. So, I can write from here e raised to power minus s t and then I can write f t over t and then dt. And if you do it carefully, then this is the Laplace transformation of the function f t by t. So, from here I can write that this is equal to Laplace transformation of f t by t. And so, it means that if I want to take the Laplace transformation of the function f t divided by some t, then I have to integrate the function the Laplace transformation of the function f t. So, this is a very important properties. Let us do one example, and suppose I want to find the Laplace transformation of a function. Suppose I take sine a t divided by t. So, this function I am just defining. I want to find out the Laplace transformation of this one. For this one I have to check that whether it is satisfying the properties or not, and why I am taking, because in this case we know that the limit t tends to 0 sin a t over t is finite. In fact, it is a. If I multiply by a here and divide by a, so this will be equal to a. So, it is a finite value, and it is satisfying the precondition that for the integration of the Laplace transformation. So, in this case what I will do, if I do not remember the formula for the integration of the Laplace transformation, then I can apply this Laplace transform directly from here, but you will see that you will not be able to find the solution because it becomes a cumbersome, very cumbersome. So, in that case we have to use this property. Now, so in this case what I do, I choose that let my f t is sin a t. So, I choose this one, and I know that if I choose this one, then in that case my Laplace transformation of sin a t will be a over s square plus a square. So, this is my Laplace transformation. Now, I want to find the Laplace transformation of my f t over t. So, in that case I will do the integration from s to infinity, and then my f s will be this one. So, it will be a s square plus a square ds. So, I can write also like this one, or otherwise I put the star here because this is the indexing. So, in that case if I do the integration of this one, so this will be equal to tan inverse s over a from s to infinity, and if I put the infinity here, tan infinity is pi by 2 minus tan inverse s over a. So, this one if I solve further, then from here I can write that this is equal to cot inverse s over a. So, that is the Laplace transformation. So, from here the Laplace transformation of sin a t over t is cot inverse s over a, provided s is greater than a. So, that is there, always there. So, this is my Laplace transformation. So, that is why it is very useful property that whenever we know the Laplace transformation of some function f t and the new function comes as a dividing by the value t, then definitely always we have to keep in mind that we have to use this integration formula. So, these all things will be useful for whenever we are going to solve the differential equations. Now, one more property is I want to use for this one. What about if I want to take the Laplace? In the last class we have discussed the Laplace transformation of a derivative of the function. If you remember that I have taken the Laplace of f dash t, Laplace of f double dash t in the last class. What about if I take the Laplace of integration of f t? So, suppose I have the integration of f t. So, like I have my function defined as this one, 0 to t I have f tau d tau. So, here I have the integration of the function f from 0 to t, and I want to take the Laplace transformation of this function. So, what will happen if I want to take the Laplace transformation of this one? So, from here the proof I can say that that what will be this one. So, so it is not a proof, it is just that I want to find out that what will be the Laplace transformation of this one. So, let I choose that my g t is the function from 0 to t f of tau d tau. So, I choose this one. Now, from here I take the derivative with respect to t both side. So, take the differentiate with respect to t both side. So, from here I will get it will be g dash t on the left side, and the right side it will be d by dt 0 to t f tau d tau. Now, in this case what is happening? I am here, I am doing the integration of the function from 0 to t, and then I am differentiating this one with respect to t. So, by the first fundamental theorem of calculus, from here I will get f t. So, this is my f t. So, from here I can say that my g dash t is equal to f t. Now, I know that the Laplace transformation. So, Laplace transformation of g dash t is equal to the Laplace transformation of f t. So, from here Laplace transformation of g dash t is what? It will be the Laplace s g of s minus g of 0 is equal to the Laplace transformation of f t. So, this is my, I can write as f s. So, from here I can find out. So, what about my g 0? So, s of g s minus g 0. What is my g? G is this one. So, if I put instead of t I put 0. So, you will say that it is integration from 0 to 0. And that value will be always 0. So, this is equal to 0. So, from here I will get s g of s is equal to f s. Okay. And so, this one. So, from here my g of s is f s divided by s. So, from here I can say, and what is my g? G s. So, it is the Laplace transformation of g, where my g is integration. So, from 0 to t f of tau d tau. So, I already know the function f t. So, I know the Laplace of f t, that is f s. So, Laplace of integration of that function is always equal to the f of s by s, where the f s is the Laplace transformation of f t. So, this function, the Laplace transformation of this function is already known to me. If I already know this one, by this formula I can find the Laplace transformation of the integration of that function. So, this is also one of the important property that we use sometime in solving the differential equation. Now, in the last class we also discussed about the unit step function, and then we discussed that the Laplace transformation of the unit step function. So, in this I will go little bit further, and you already know that we in the previous classes I have discussed about the Dirac delta function. So, Dirac delta Dirac delta function, we already know that this is equal to, that is equal to 0 when x is not equal to a and infinity when x is equal to a. So, that we already know. Now, what I do? I want to find out the Laplace transformation of the Dirac delta. So, what about the Laplace transformation? So, Laplace transformation, I will apply the Laplace transformation for this function e raised to power minus s t dt. And if you remember that whenever I have some function f t multiplied by the Dirac delta function, and doing the integration, then we already know then this is always equal to the function, the value of the function at the point A. So, from here I can say that the Dirac delta, the Laplace transformation of the Dirac delta is always equal to e raised to power minus S A, where S is greater than 0 I can take. So, this is the Laplace transformation of the Dirac delta function. So, now after find out the Laplace transformation of the Dirac delta, so let us do the some application of the Laplace transformation. So, let us take first one, the example I just take one. I have a differential equation y double dash minus 3y dash plus 2y is equal to f t, and f t is given to me as a function 1 when t is, its value is 0 when t is, and its value is 1 when t is equal to 2 infinity. So, this function is given to me in this form. So, if you want to find out the solution of this second order linear differential equation, you can apply the method, but if you see on the right hand side, the function f t is not a continuous or differential function as we were doing for in the previous classes, but this is a piecewise function. And if you see this function if I plot, so it is t and this is my f t. So, from 0 to 1, suppose 1 is this, 2 is this one. So, from 0 to 1 its value is 1, because it is open on that 1, and then from 1 to 2 its value is 0, and from 2 to infinity its value like this. So, in this case my function f t is given to me in this form. So, it is a piecewise continuous form. So, in this case if I want to solve this differential equation using the previous methods, then we do not know that how to apply how to find out the, because in this case I am able to find the solution for the homogeneous part, that I can put equal to 0 and then I will solve this one. But what about if I want to find a particular solution? So, in the particular solution, you know that we have applied the operator theory to find out the particular solution or the variation of parameter. So, in that case we do not know what will happen if I have the function f t on the right hand side in the form of a piecewise continuous form. So, in that case this method is, this differential equation seems to be very difficult if we want to apply the previous method, but if I have the knowledge of the Laplace transformation, then you will see that it is very easy to find the solution for this type of differential equation. So, what I do is that, and now in this case you know that my function y t is well defined, I assume that, and between the t belongs to 0 to infinity. So, that should be there, that my t should be the function y t should be well defined and of the exponential order for all t from 0 to infinity, because this is there only then I can apply the Laplace transformation. And I also consider that the Laplace transformation of the function y t is y s. So, this one I already assume. So, from here what I will do that this equation number 1, I take the Laplace transformation, apply. Laplace transformation to both sides of equation 1. So, in that case I will take the Laplace transformation. So, Laplace transformation of y double dash minus 3y dash plus 2y equal to Laplace transformation of f t. Okay. Because the Laplace transformation, if you see, whenever I take the Laplace transformation of the derivative, then the value of the function and its derivative at some point should be known to us. Then I take the initial problem. So, from here I also define that y at 0 is 0 and y dash 0 is also 0. So, this is my initial value problem and I am taking the initial value as y 0 at 0 and y dash 0 is 0. Now, I apply the Laplace transformation. So, because I know that the Laplace transformation is a linear transformation. So, from here I can apply. Now, my f t is there. So, first of all I will apply try to make the write the function f t in the form of a single function with the help of a unit step function. So, in this case what I will do, my f t I can write in this form as 1 plus then 0 minus 1 this minus this and defining the unit step function at the point which is common to both plus this value minus this value. So, 1 minus 0 and then unit step function u at 2. So, from the left hand side I will get s square y s minus s y 0 minus y dash 0. So, this is my Laplace transformation of y double dash minus 3 and then the Laplace transformation of y dash will be s y s minus y 0, okay, plus 2 times the Laplace transformation of y, that is already known to me, that is y s, and on the right hand side I want to take the Laplace transformation of the function. So, this function can be written as 1 minus u t minus 1 plus u t minus 2. So, this Laplace transformation I want to define, and just to verify that whether we have written this function correctly or not, you can check the value of the function for different value of t. Like I have a value whenever t belongs to 0 to 1, in that case this value will be 0, this value will be 0, you will get only 1. When t lying between 1 to 2, so this value will be 1. So, in that case this 1 minus 1, so it will be 0 and this will be 0, the value will be 0. When t is lying between 2 to infinity, in that case this will be 1, this will be 1, so the value will be 1. It is okay. Then from here the Laplace transformation of 1 is 1 over s minus, and I want to define the Laplace transformation of unit step function at t at equal to 1. So, this is a unit step function. So, I know that the Laplace transformation is e raised to power minus s over s in this case, and in this case my Laplace transformation will be e raised to power minus 2s by s. So, this is the Laplace transformation we are defining here, and you can also see that just now we have calculated the Laplace transformation of the direct delta function. So, that was e raised to power minus as, but here we are dividing by s. So, that was the Laplace transformation of the unit step function. So, from here I just find out the solution. This value is 0, this is 0, this is 0, that we have chosen to make it simpler. So, from here I will get my it will become s square minus 3s plus 2 ys. This is 0. So, we will get this value, and on the right hand side we will get this one. So, from here my ys becomes, so this value I can take on the right hand side. So, this will be 1 over s minus e raised to power minus s over s plus over 1 over. So, this one I can make as a factor. So, this is coming as s square. So, this will be s minus 1 s minus 2, because if you see from here it will be s square minus 3s plus 2. So, this is my ys. Now, I want to solve this one. From here I will get that if I multiply this factor, so my ys I can choose as here 1 over s minus 1 s minus 2 minus plus e minus 2s s minus 1 s minus 2. So, this is the factor we are taking here. Now, I wanted to find the Laplace transformation of this factor. So, from here I will use the partial fraction. So, this factor s minus 1 s minus 2, it can be written as using the partial fraction. So, I can write this as 1 over 2s minus 1 over s minus 1 plus 1 over 2 s minus 2. So, using the partial fraction I can write this fractional part in this form, because whenever we are solving this type of differential equation, generally we have to apply the partial fraction to make this, because only then I am able to take the Laplace transformation, inverse Laplace transformation. So, from here I am able to find this value. Now, suppose I want to find the Laplace inverse of this one. This value, and I know that the Laplace inverse is also linear in this form. So, it will be 1 over 2 minus e raised to power t plus 1 by 2 e raised to power 2t. So, this is my inverse Laplace of this function. So, from here I can define the Laplace inverse of e minus s divided by this factor, again s minus 1 s minus 2, and this one I can take similar way. So, it will be again L inverse of e raised to power minus s over s 2s minus e raised to power minus s s minus 1 plus e raised to power minus s 2 s minus 2. And you from here you can see that I have a function of s, and that is being multiplied e raised to power minus s. So, if you remember, then this form leads to that the use of somewhere we are using the unit step function. So, from here if I want to take the Laplace transformation, inverse of the Laplace transformation. So, the Laplace inverse of e raised to power minus s over 2s. So, this if you take this one, it will be half u t minus 1. Laplace of this one, it will be e t minus 1 u t minus 1, because the Laplace 1 over s minus 1, if I want to take the inverse, it is e power t, but I have a factor e to power minus n. So, it is a unit step function, and we know that this is becomes f t minus 1. Then Laplace inverse of this function, it will be 1 by 2 e raised to power 2 t minus 1 u t minus 1. So, this will be there. So, from here if I find out the Laplace inverse, if I just write here directly, then Laplace inverse of the whole factor s minus 2 will be, in this case it will be equal to 1 by 2 u t minus 1 minus e t minus 1 into u t minus 1 plus half e 2 t minus 1 u t minus 1. So, this will be the inverse of the Laplace transformation for this factor. So, from here, and the same way I can go for the another one, only thing difference is that if you see it clearly, then here only we are multiplying by e to the power minus 2s. It means the unit step function has the value at so a is equal to 2 in that case. So, from here now ys is equal to the factor we have taken. Now, I want to find the f t. So, f t in that case will be, the solution in that case will be y t will be, so I can write my factor now, half minus e t plus e 2 t by 2, and then the inverse minus. So, I can take u t minus 1 common here from this one. So, it will be half minus e raised to power t minus 1 plus half e raised to power 2 t minus 1 plus the last factor. So, that will be unit step function defined at 2. So, this will be half minus e t minus 2 plus half e 2 t minus 2. So, from here this one. So, that is my ultimate solution of the given differential equation when the right hand side function was the piecewise function. So, from here I can say that my solution y t will be, I can write this function in the piecewise form. So, this will be equal to half minus e t plus e 2 t by 2 when t is 1, because this factor will be in that case. So, now then whenever I have t so in that case it will be the same factor half minus. So, in that case this value will be 1, and then I will get this value. T minus 1 plus half e 2 t minus 1. So, this is the factor when t is 2, and then whole value will be equal to always. So, this will be half minus e t minus this factor plus. So, I am taking now the when the t is greater than 2. So, t is greater than 2, its value will be 1 and then it will be equal to half minus e raised to power t minus 2 plus half e raised to power 2 t minus 2. So, this is equal to the t. So, from here you can see that this function, if you see that this functions is almost same here in this case, only we are transferring this to by 1 on the right hand side and then again transferring this one to the right hand side by the 1. Otherwise, we have the same function, but it is just doing the transformation by 1 and again 1 and we get this solution. So, that is the solution of the corresponding differential equation we were trying to solve. So, today we are trying to find out the solution of a differential equation where the right hand function was a piecewise function. So, in the next class we will go further and try to find out the application of the Laplace transformation for other problems. So, thanks for watching. Thanks very much.